am Dr. Pavitra Bharadwaj, Associate Professor in the Department of Computer Science, Jesus and Mary College, University of Delhi. So friends, in the last lecture we have been talking about deadlocks, that what is a deadlock situation and what are the conditions because of which deadlocks can occur. So we had seen that basically a deadlock will occur when a process is waiting for a resource which in turn has been acquired by another process, and the other process is also waiting for a resource which is acquired by some other process, right. So we had seen that there are four main conditions which can which when occur simultaneously in a system, they will cause deadlocks, right. The four conditions that we had discussed, which are termed as necessary conditions for a deadlock, they are mutual exclusion, no preemption, hold and wait, and circular wait, right. Now in order to describe the deadlocks more precisely, and in order to look at deadlocks in in a more pictorial method or in a graphical method, another tool is very commonly used, which is actually a directed graph. And this tool or this graph is known as a system resource allocation graph. That is how resources are allocated in a system, this graph is going to show. Now as like other graphs, this graph will also have a set of vertices which is V and a set of edges, that is E. Now the vertices can be partitioned into two types of nodes, that is node type P, which is a set of all the processes in the system, and the set R, which is a set of all the resource types in the system, right. So these will be, P will have all the processes, say P1, P2, Pn, R will have all the resources which are available in the system, say R1, R2, Rn, right, and there will be a set of edges which will connect the nodes P type to the node R type. So there will be a directed edge from process Pi to resource Rj, right. So there will be an arrow from Pi to Rj, and this will signify that process Pi wants an instance of the resource Rj, and it is currently waiting for that resource. So this type of arrow is known as a request edge, right. This is because Pi has requested the resource Rj, right. There can be a directed edge from the resource Rj to the process Pi, right. This signifies that an instance of the resource Rj or the resource type R has been allocated to the process P. So this is known as an assignment edge. So the edge from the process to the resource, which denotes a request that the process has requested but is waiting, is known as a request edge, and the edge from the resource to the process is known as an assignment edge, which shows that the resource has been assigned to the particular process. So if we look at the the node, the symbols, so a resource is shown with a rectangle, and inside the rectangle we see the number of dots. So each dot represents one instance of the resource. Say for example, this is a resource R and there are 3 dots. So this means that there are 3 instances of the resource in the system, and there is a circle which shows the process P. So circles shows the processes and the rectangles show the resources, and within the rectangle the dots will show the instances of the resource which are available in the system. Now when a process, say Pi, will request an instance of the resource Rj, so there will be a edge, a request edge, which will be inserted into the resource allocation graph. When this request can be fulfilled, that is the request, the resource can be given to the process, then instantly the assignment edge will be created from Rj to Pi. when the process no longer needs the access to the resource, then it will release the resource, and then finally the assignment edge will be deleted. So, we will make multiple stages of the resource allocation graph to see, right. So, in this resource allocation graph, actually we are looking at 3 sets. The first set is the set P, that is the set of 3 processes P1, P2 and P3. The set R, which has got 4 resources R1, R2, R3 and R4, and the set of edges which has got edge P1 to R1, P2 to R3, R1 to P2, R2 to P2, R2 to P1 and R3 to P3. So, what we are saying that these are the edges which are created in the resource allocation graph. And what are the instances? What are the number of instances of each resource? So, R1 has got only 1 instance, R2 has got 2 instances, R3 also has 1 instance, and 3 instances are there of resource R4. So, if we look at the resource allocation graph here, we can see that there is an arrow which is going from P1 to R1. So, this means that the process P1, it wants the resource R1, but there is an arrow from R3 to P1. So, this means that P1 is holding an instance of the resource R2, but it is waiting for an instance of the resource R1. Likewise, process P2 is holding an instance of the resource R1 and it is waiting for an instance of the resource R3, and process P3 is holding an instance of the resource R3. So, we can see that this graph actually shows that which process is waiting for which resource and which process is holding on to which resource. And as you can see, you have multiple instances here, like for example, R2 has got 2 instances. So, one instance has been assigned to the process P1, the other instance has been assigned to the process P2, and R4 is not yet assigned, not yet requested. So, R4 stands there alone. Now, given the definition of the resource allocation graph, we can see that if the graph has no cycles, right, if there is no cycle in the graph, then we say that no process is in the deadlock. But if the graph has a cycle, then we say that a deadlock may exist. Please understand, when there is a cycle, we say that a deadlock may exist. It is not necessary that if a cycle is there, a deadlock will be there. We will see how this can occur, right. So, if we say that each resource has only 1 instance, right, then a cycle will imply that the deadlock has occurred, because every resource has got 1 instance and it is waiting for the other resource. So, this wait will never end. If the cycle involves only a set of resource types, each of which has a single instance, a deadlock is bound to occur. So, each process involved in the cycle is said to be deadlock, right. So, therefore, in this case where there is only 1 instance of each resource, then a cycle being present in the resource allocation graph is both a necessary and a sufficient condition for existence of the deadlock, right. But if there is a situation in which each resource has got several instances, right. So, then in that case a cycle will not imply that a deadlock has occurred, right. So, cycle will be there, but still there is no existence of a deadlock. So, therefore, we say that existence of a cycle in the resource allocation graph is a necessary condition, but it is not a sufficient condition. Sufficient conditions means that there has to be 1 instance of each resource and a cycle, both the things have to be there. If there are multiple instances, so even if we see a cycle, there is no deadlock between the processes, right. So, now in order to understand this, we will again go back and see the resource allocation graph which is here, right. So here we see that process P1 is requesting the resource R1 and it is holding the resource R2, and process P2 is also holding another instance of the resource R2 and it is being given the resource R1. So although we see that there is a cycle here, we see that there is a cycle from P1 to R1, from R1 to P2, from P2 to R2 and then R2 to P1. There is a cycle here, but this cycle does not mean that there is a deadlock. Why? Because R2 has got two instances. So one can be given to P1, the other can be given to process P2, and hence both the processes P1 and P2 will execute. Then nobody has to wait for the freeing of the resource R2 because there are multiple instances. There are two instances in this case. So therefore we understand in this case that although there are cycles which are existing, P1 R1, P2 R3, P3 R2 and then P1, still P1, P2 and P3 are deadlocked. Process P2 is waiting for the resource which is held by process P3, right. So even minimal cycles are there, then also it will be a problem. Okay. So process P3 now we see is waiting for the process P1 or process P2 to release the resource R2, because both P1 and P2 are holding one instance each of the resource R2. Now in addition, P1 is also waiting for the process P2 to release the resource R1, right. So now what is the graph that we see? We see that the graph is P1 R1, P3 R2 and P1, right. So this is, there is a cycle in this graph, but there is no deadlock. As we can see, there is a cycle in the graph because P4 is P4 has got the resource R2, okay, and P3 has requested for R2, P1 also has R2, right. So therefore P1 can execute with R2 whenever it will get R1. So therefore in this graph we see that there is a cycle but there is no deadlock, right. So this is about how processes, how resources and how the allocation can be studied very specifically, very easily and clearly using the graph, right. Now besides studying the conditions, besides studying the allocation, it is also very important that we look at methods for handling the deadlock. Now generally speaking, the system, the various pedagogies or various lines of thought, they deal with the deadlock problem in three ways. So the first way or the first approach to handle deadlock is that you prevent the deadlock, right. That is, we avoid the deadlock. That is, we ensure that a deadlock will never occur in the system, right. That is, our system will not allow deadlocks to occur. So this is known as prevention or avoidance. Second is that we can allow the system to enter the deadlock, detect it, and then we will recover from the deadlock. So this is the second approach where deadlocks can occur, but they have to be detected and recovered from. And the third approach is that we completely ignore the problem. Ignore the problem means this is called the ostrich approach. That is, we will just like an ostrich buries its head inside the sand and thinks that there is no problem. Likewise, we will also assume or we will also pretend that deadlocks will never occur in the system. That is, we will completely ignore. Now the third solution, that is complete ignorance approach, actually is used by most operating systems like Linux and Windows. So what is the problem now? It is the department or it is the responsibility of the application programmer to write programs which can handle deadlocks. So instead of the operating system bothering about deadlocks, it is the application programmer who has to worry about deadlocks occurring and handling. Now the first two strategies. This is the first strategy that we talk, that is prevention and avoidance, right. So if the system has to ensure that deadlocks never occur, right, then they can use either a deadlock prevention or a deadlock avoidance scheme, right. Now prevention will provide a set of methods to ensure that at least one of the necessary conditions cannot hold. We said that the four conditions, that is mutual exclusion, no preemption, hold and wait, circular wait, all the four conditions must exist simultaneously for a deadlock to occur. So if you want to prevent a deadlock, then you need to make sure that these conditions, at least one of these conditions does not happen, but does not hold. So these methods, they prevent deadlocks by actually constraining how requests for resources can be made. So basically they will see that the four conditions are not met when we are talking about prevention and avoidance, right. So when we say deadlock avoidance, then in that case the operating system will be given additional information in advance concerning which resources a process will request and use during its lifetime. So before a process starts, the operating system is informed about all the resources which the process may require. So when the operating system will have this additional knowledge, then it will decide for each request whether the process should start or whether the process should wait, right. So when the operating system is deciding that whether the current request can be satisfied or it must be delayed, then the system has to consider all the resources which are available to it the present time, right. So the resources which are currently allocated to each process and to the future request and the release of each process. So all this calculation has to be done. If you are talking about avoidance, all this calculation has to be done by the operating system before actually the process can be allowed to start. So if a system, it does not employ either a prevention or an avoidance algorithm, then what will happen? Then definitely a deadlock situation will arise, it will occur, right. So in this environment where the system can provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, and then we need to have another algorithm to recover from the deadlock. If there is no such algorithm, in the absence of these detection and recovery algorithm from deadlock, then what will happen? There will be a situation in which the system will be in a deadlocked state, because you are neither able to detect a deadlock nor you are able to recover from the deadlock. So what will happen? The system will be stuck, right, and in that case there will be no way of recognizing that what has happened, why is the system not functioning. So in this case where we are looking at an undetected deadlock, right. So it will definitely cause the system's performance to deteriorate, right, because why? Resources are being held up by the processes which are not running, and more processes are making the request for the resources, and therefore more and more processes are entering into the deadlock state. So eventually the system will stop functioning and it will need to be restarted manually. Now surprisingly, most operating systems, they go for this approach. This approach becomes a more viable approach, that is, the systems, they have no planning, they have no algorithm to detect or recover from deadlocks. Why? Because this is very expensive. It is very expensive to create such algorithm, and also because the possibility of a deadlock is very rare. Say once a year the system will go into a deadlock situation. So therefore it is cheaper for the systems to get into a deadlock once a year and restart the processes, instead of going for the detection and then recovery algorithms. So what is done? The systems are allowed to go in the rare deadlocks, in the exceptional conditions of deadlocks, and then they can be manually restarted. Right, because there are also conditions, besides deadlock, we also say that sometimes the systems, they go in a frozen state, right. So, what is frozen state? Frozen state is different from a deadlock state. In frozen state, the system is, it is there is a thread basically, which is like, for example, in real time processes, right. There is a high priority process which is, in a non-preemptive scheduling mode, and that is not returning the control of to the operating system. It is holding the CPU and not returning the control. In such cases, it is not a deadlock, but it is called as a frozen state, and in this case also we will use the manual recovery method, that is, the system will be manually restarted or the process will be killed by the task manager. So, the idea here is that deadlock detection and recovery are non-viable options. So, what is commonly followed? The strategies commonly followed are deadlock prevention and avoidance, or otherwise the third strategy, that let the deadlock happen, or the system assumes that there is no deadlock, we pretend as if there is no deadlock and the system is running fine, right. So, when we talk about the first and foremost, that is the deadlock prevention approach. So, the first way of ensuring that deadlocks do not occur. So, we had discussed that we will see that at least one of the necessary conditions does not hold, right. So, if you want to prevent the occurrence of a deadlock, you can prevent that the 4 conditions, out of the 4 conditions, at least one does not occur. So, the first condition was the mutual exclusion condition. Now, in mutual exclusion condition, at least one resource has to be non-shareable, because shareable resources will not require mutually exclusive access, and therefore, they cannot be involved in a deadlock. Like, for example, read-only files. Read-only files are a very good example of shareable resources, because several processes, they can open the file, and because it is in the read-only, so they can be granted simultaneous access to the file, right. So, they don't know, no process has to wait for a shareable resource, right. However, there can be resources which are intrinsically non-shareable, like, for example, mutex logs. So, that is a different thing, but the resources which can be, available in shareable mode, they will definitely, they do not require a mutually exclusive access to be granted, right. So, therefore, this approach cannot, this approach can definitely avoid deadlocks. Then the second condition, that is hold and wait. Now, hold and wait basically means that the process is having some resources and it is waiting for the other resources, right. So, whenever a process requests a resource, it does not hold on any other resource. So, we have to see that, there are different protocols which we can use for hold and wait. So, in one protocol we can use, the use requires each process to request and be allocated all the resources before it begins execution, right. So, basically what is happening, a provision is to be made where a process will send a system call and all the processes which are required by this process are preempted. The alternative protocol would be that a process requests the resources, only the one which it requires, right. The process requests some resources, it uses them, then it requests an additional resource, and then it will release all the resources that it is currently allocated. That is, the process is not going to hold on to all the resources at the same time, but it will only request the resources which it needs at that very instance of time. Now, a very good example can be given to understand these two, difference between these two algorithms. Say, for example, there is a process which requires to copy a file, okay, from the DVD drive to the disk, and then it will sort the file, and then the result is to be printed on the printer. So, if we say that the first approach, then before the process starts, it will ask for the DVD drive, it will ask for the disk drive, and it will ask for the disk file, and it will ask for the printer. Till the time all three are given, the process will not start. But if we use the second algorithm, in that case first the system will ask for a DVD drive, it will ask for the file, the disk file, it will copy from the DVD drive to the disk file, then it will release both the DVD drive and the disk file. Then it will again ask for the printer and the disk file, and it will give the print command. So, in this it is holding on to two resources only at a given time. But actually in both these approaches there is a major disadvantage that the resource utilization remains low. Resources are allocated but they still remain unused. Also there is a problem of starvation. That is, a process which needs several popular resources will have to wait indefinitely, because at least one of the resources that it needs is always allocated to some other process. So, there is a problem of starvation also which is associated with this. Then the third condition, if we look at, that is the condition of no preemption. So, in this case the third condition, that is no preemption, means that the resources which are given, they can be preempted. So, if a process is holding some resource and it requests another resource, that cannot be immediately allocated to it. That is, the process has to wait for the resource. Then all the resources the process is currently holding are to be preempted. They are taken back, right? That is, the resource which are implicitly released, all the resources are released and the preempted resources are added to the list of other resources, right? Alternately, there is another approach that if a process requests some resources, the availability is checked. If they are allocated, then they check whether they are allocated to some other process. If they are being held by another process, those processes are preempted for this. So, in no preemption, if the resources are not available or they are held by waiting process, the requesting process has to wait. While it is waiting, some of its resources can be preempted to another process. The last condition is the circular wait condition, in which each process is waiting for a resource which is held by another process. So, in this case also we can solve, or we can allow that this does not occur by assigning a number, an incremental integer to each resource, and the processes can only ask for the resources based on their incremental number. So, that a resource which is higher in increment can only be asked when a resource which is lower in number is given. So, these are the four conditions which the system tries to evade in occurrence, in simultaneous occurrence, in order to avoid the occurrence of deadlocks in the system. So, the deadlock prevention strategy this is. So, friends, we will be continuing with our discussion on deadlocks in the following lectures. Till then, please keep watching CEC. Thank you.